Okay, so for the fourth question, last question we have, it says that in the early days of radio, AM signals were demodulated by a crystal detector followed by a low-pass filter and a DC blocker. So that's the diagram we have. Let me sketch that. So we have an AM signal as the input, AMT, and this goes into a squaring device. As you can see, this part is given in the question, this diagram. Then this goes into a low-pass filter, and the output of the low-pass filter goes into a DC blocker. And then we have the output YT. And these points are shown as point A, B, C, and D. Assume a crystal detector to be basically a squaring device. Determine the signals at point A, B, C, and D. Point out the distortion term in the output YT. Show that if A is much larger than the MT, the distortion is going to be small. Alright. Now, we know for the amplitude modulation, we know in which form the signal we have at point A is going to be. It's going to be A plus MT times cosine omega CT. Okay, this is the generalized amplitude modulation signals formula. So as we transit through point A to B, we have a squaring device, so we need to take the square of whatever we got at point A. So at point B, our signal is going to be this: A plus MT times cosine omega CT square, or it's going to be A square plus 2AMT. I'm just taking the square of these terms, plus MT square times cosine square omega CT. Okay, this is the signal we got at point B. And if we apply a couple of modifications to this formula, first we need to convert this cosine square by using this conversion 1 over 2, 1 plus cosine 2 omega CT. That's the conversion of cosine square. So at point B, now we have A square plus 2AMT plus M square T times 1 over 2, 1 plus cosine 2 omega CT. Now our low pass filter, are we given with this frequency? Okay, I can't see it, but probably should be shown or given in the question that the low pass filter is centered at omega C. So it's only able to pass through the frequencies lower than omega C, but higher frequencies are going to be cancelled out. As I said, this should be given in the question, but probably is missing. So since our low pass filter can only pass through the frequencies lower than omega C, as you can see, this cosine has a frequency of 2 omega C. Since this is higher than the low pass filter, it's going to be cancelled out by the low pass filter. So at point C, our signal is this. We got only 1 over 2 here. A square plus 2AMT plus M square T. Okay. Now, if we just rearrange this one more time, I'm just going to take A square over 2 terms, or sorry, A square terms outside. So the signal at point C is going to be A square over 2. We only A left here, 2MT over A plus we got the M square term also, so it's going to be MT over A square. Nice. I just take an A square term outside, so these are the remaining terms inside. Now the question was asking that if A value is much larger than the MT. Now here we got that ratio. As you can see that if A is much larger than MT, we are also taking the square of this ratio. Let's say MT is 1 and A is, let's say, 1,000,000. These are just some random numbers. This ratio is going to be small. And if you take the square of this ratio, it's going to be much smaller than this one. So this term can be ignored because of this. A is much larger than mt, so this ratio is going to be small. And if you take the square of this small value here, we can ignore that. It's going to be much smaller than this ratio here. So only remaining terms is now a square over 2, 1 plus 2mt over a. Right? This is what we're left with. Okay. Just a minute, I'm going to check one or two things. Okay. Now if I multiply this with the terms inside these brackets, we got a square over 2. This is one of the terms we obtain on the output, plus these 2's will cancel out each other, a will cancel out each other, a times mt. Now this is a DC term, because we got only amplitude value, it's going to be like 4, 6 or whatever the value is for a, but this is a DC term. We don't have any MT signal right next to it, no carrier, just a coefficient. And if you check the diagram here, after the point C, after the low pass filter, at point D, as from the transition from C to D, we have a DC blocker. So this term, this DC term is going to be blocked by DC blocker. Blocked by DC blocker. So as we go from point C to point D, this term will be cancelled out by the DC blocker. So only thing left for the output is going to be A times MT. This will be the output. So as a brief summary, we got this diagram here. We have an AM signal as the input, and we are putting all these signals into these blocks: a squaring term, a low pass filter, and the DC blocker. Now this was the input signal at point A. This is a generalized formula for an amplitude modulated signal. Then from point A to B, we are taking the square of this term. So this is what we have done at this point. So here we obtain the cosine square term. So we applied the trigonometric conversion here. So we converted this cosine square into this. Now from point B to C, we have a low pass filter whose frequency is omega C, meaning that frequencies higher than omega C are going to be filtered out by the low pass filter. As in this case, we have a cosine with a frequency of 2 omega C. So this part is going to be filtered out by the low pass filter. Now these are the remaining terms. We just applied a couple of modifications here. We took the a square term outside, and we obtained these three terms. We got 1, we got 2 mt over a, and mt over a square. Now the question was saying that if the a value is much larger than mt, as in this ratio here, the denominator is going to be much larger than the denominator. So the ratio you are going to obtain here is going to be quite small. After you take this small value square, it's going to be much smaller. So we can ignore this term here. So the remaining terms are going to be a square over 2, 1 plus 2 mt over a. So if I distribute this multiplication inside, we are going to obtain two terms. First, a square over 2 times 1 here. Then a square over 2 times 2mt over a. And this yields this result. This is a DC term. There's no MT signal, there's no carrier, nothing. This just, you can think of it as just a coefficient because a value is going to be an integer. So this is a DC term. As we go from point C to D, we have a DC blocker. So this term is going to be blocked by the DC blocker. So the remaining term will define the output YT.